It's afternoon where I am, but good morning. Can you see my screen now?
It's slowly coming up.
Okay. I'll make sure I can bring over the chat here, hopefully. Okay, great. And I'll probably turn off my camera here shortly to save up some bandwidth. Are we good to go then, Tim?
Looks good.
Looks good. Looks good. Looks good.
All right, great. Well, good morning, afternoon. I don't know if there's any good evening to anybody on the call here today, but I'm happy to be here, and I'm happy to talk to you about what MPP is and really how it relates to a Synapse SQL pool and its architecture, and how it's different from just a really big SQL server. We've heard some people talk so far today about some pretty detailed things. I don't know how many people on the call are as familiar with the architecture of a Synapse SQL pool. But I have heard some references to things around it, so I think it's probably good to explain it. I'm going to be very general here. It's going to be very much kind of high-level architecture, which is really good because our next speaker, Mark, is going to be talking about some of these concepts in more detail. And so this is kind of like the 10,000-foot view of a Synapse SQL pool. And so now, just to be aware of any bandwidth issues, I'm going to make sure that I come over here and turn off my personal camera if I can find it. Right over here. Great. So my name is Jared Karney. I live in Chicago, and I'm a senior customer engineer with Microsoft. I've been working with SQL Server and data and analytics and statistics and all this fun stuff since probably about 2005. But I really just started to get more and more into analytics from the data side. And so when I talk about a Synapse SQL pool, I tend to talk about it with regards to SQL Server. So you may hear me use some analogies there, and I'll probably do very well with responding to any questions as they relate from SQL to a Synapse SQL pool. So what we will talk about today is we're going to first start out outside of the Microsoft or the Synapse kind of environment. We're just going to talk about the difference between SMP and MPP, and that would be the symmetrical processing versus massive parallel processing. Then we'll talk a little bit about more specific Synapse SQL pool architecture. We'll talk about table geometries and indexes as that falls under the architecture, and then finish up just really quick with a little bit on data movement. And there'll definitely be a deep dive after my talk in the next session. Great. So let's start out talking about SMP versus MPP. So first of all, let's define what SMP is. So SMP is symmetric multiprocessing. When you think of Azure SQL DB, Azure SQL Managed Instance, SQL Server on a VM, SQL Server Postgres, almost all of these relational database platforms are symmetric multiprocessing. And all that means is that we have one or more CPUs that are used to run parallel tasks with shared resources. More specifically, there's a shared bus for memory, I/O, and network. Now, some of you may have heard of something called NUMA, which is non-uniform memory access, where we say that a particular CPU has access to certain banks of memory, and this other CPU over here has access to these banks of memory. And so they do have some type of kind of dedicated bus there, but they also have the ability, which is why it's this non-uniform memory access, to touch each other's memory and access each other's memory. Right? Another way of thinking about this is even if we have many CPUs, they're all on a single motherboard, right? That's kind of another way of looking at it. And so when we're accessing storage, each CPU has just as much right or just as much access to the underlying storage or memory. And so, as I mentioned, most of our OLTP databases or our traditional applications and database platforms are SMP. So now let's talk about what is the other side of this? And that is the MPP, or massive parallel processing. So in this case, we are taking more than one CPU and ultimately creating compute nodes. And that, as somebody who doesn't necessarily study lots of different MPP architectures, that's typically what we talk about when we're talking about Spark or Synapse SQL Pool, PDW or APS, which is the Microsoft on-premises product that this is based off of. So the idea is that they're separated from each other, and that way they each can run their own parallel tasks. So they're still using parallelism within the CPU, but they each have their own set of tasks. In fact, they don't really know about each other. And part of that paradigm is that each node is going to have its own resources. This is known as shared nothing, right? So that the storage that I am hitting with a particular node is not attached to the other node's storage. So we have to have some type of mechanism or architecture to bring those together at some point, because we're treating this as a single database. And so part of that architecture does come with each node being connected to each of the other nodes, and typically a control node through some type of high-speed networking. So that is the difference between SMP and MPP. Now, why do we have a need for MPP? All right, so of course, MPP, as I said, it stands for massively parallel processing. And when we think of that word massive, we're thinking of big data usually in this particular case. And if it's not necessarily big data, which is kind of an ambiguous term these days, it means that maybe we have a lot of computations. We need a lot more processing. But in general, we are talking about massive amounts of data. And so we're trying to split up the workload even more so than we do with typical symmetrical parallel processing. So sometimes when we talk about parallelism in an SMP architecture, we talk about like jelly bean counting and putting people in a room. And I've got a pile of jelly beans and I ask different people to count it. More so, maybe the way that I'll talk about this in the context of MPP is that SMP is more like me having two hands, and I'm using two hands to move the jelly beans. And then if we take that up a level to having the people in the room, that may be more where the individuals become more like MPP, because each person has their own stack of jelly beans that they're counting. The two hands are doing the work with the same pile. Each one is doing their own counting, and then we're able to come back to whoever is leading that group and pass on our information to them. So that's another way of kind of thinking about it, right? It's a team approach. Now, part of that type of architecture means we need to have a different method for scheduling our tasks. We need to have something to allow these things to talk to each other, the nodes to talk to each other. We need to have something that can come up with a plan as to how we're going to access the data on each one of these different nodes. If they're not shared data, something needs to know what to request from each one of those for their work to do and needs to keep track of that. We're also going to need to think a little bit more about our own architecture. How do we architect our databases, our tables, our indexes to work with this and take advantage of this architecture? So this is kind of a nice diagram just illustrating where in the SMP architecture here, and I like to switch to my laser pointer. So this here is SMP, where we might have multiple CPUs sitting on a particular motherboard or server, right? Each one of those CPUs has their own level of cache, but they all access, for the most part, the memory and the I/O through a shared bus. And so we can get issues there just because of bandwidth, right? Because they're both, everything is competing to get through the same pipe. Whereas on the right, we've split that up even more. We've kind of partitioned that workload at another level. And then if we need to share data between these nodes, which you'll see that's called data movement as we move on, we've got the high-speed interconnect to do so. So now that we understand the difference between SMP and MPP, we'll take a look at how Synapse SQL Pool is architected to work this way. So when you create an Azure Synapse SQL Pool, we will always have one control node. And that control node sits at the top of the hierarchy, and it is going to make the decisions and hold the information necessary to push our SQL down to these other nodes. In between these other nodes known as compute nodes, we have this layer called the MPP engine. And it's not necessarily separate, but it's what's doing the coordination between the control node and the compute nodes. We also have something there called the DMS, or the Data Movement Service. Data Movement Service, along with instant data movement, is how we allow these nodes really, I don't want to say to communicate, I'm going to say move data between them. And we haven't really touched on what that means, but understanding that a single database or even a single table is broken up between these different compute nodes, we're going to have a way to maybe bring them together. Data movement basically happens with joins, and we'll talk about that in a little bit. And then at the bottom, we've got our storage layer. And the trick here is that the storage layer is completely decoupled from the compute nodes, in the sense that it can be disconnected very easily. Now, what you'll see on this particular slide is 60 little containers or buckets. And that's because in Azure Synapse SQL Pool, we always have what we call 60 distributions. At the end of the day, what these are 60 Azure SQL databases. And the reason that we always have 60 is because it allows us to do really cool things when we need to scale up or scale down. So in this particular case, okay, this would be considered, and we'll talk about data warehouse units in a little bit, but this particular case shows 4 nodes. And so if we have 4 nodes and we always have 60 distributions, what that means is that we get 15 distributions for each compute node. Or another way of thinking about this is when we set this up or when we start it up, we are going to attach 15 databases on the first node, 15 databases on the second node, 15 databases on the third node, and 15 databases on the fourth node. And so if we wanted to scale up or down, and I do see a question there, we'll get to that in a moment.
Okay.
If we wanted to scale up or down, we do have to take this offline at this point, but what we're doing is we are shutting down all of those SQL DBs and then either provisioning more compute nodes and then just reattaching these databases in a different ratio of compute node to distribution. Or if we're scaling down, we're simply removing some compute nodes and then again, reattaching databases according to that ratio. One of the questions that are over here in the chat is the control node affected by Azure scaling? I.e., is it reset after a scale? That's a good question, and I'm not 100% sure what you're asking about in that regard. But if you're talking about things like caching, as we typically have in a SQL server, right? Plan cache and data cache, yes, those types of things are going to go away. Now, is that at the control node? Not really. We'll talk about what's at the control node in actually the next slide. Did that answer your question, Rick? I guess, okay, yes, thank you. Great. So one of the nice things about this is it makes provisioning scaling very quick. Do we have to take this at this point in time offline? Yes. But it becomes pretty fast because the storage is not moving. We don't have to, scaling up doesn't require us to split our data into more pieces. That's the whole idea here. This architecture makes it very easy to detach and reattach because the storage is completely decoupled, not just from the nodes, but from each other. Okay. So let's talk about what is at the control node. So the control node does host the data movement service. The data movement service, or DMS, is legacy. Ultimately, it has its own kind of buffer layer and service layer, and so it can become a bottleneck when the control node is taking a query, parsing it, and it has to move data maybe around during the execution of a query to satisfy things like join conditions and stuff like that. What we typically do now is something called the instant data movement, which ultimately breaks it down into individual SQL queries and runs those in order to get data to move it around. Okay. Polybase also still uses the data movement service. And Polybase is used quite commonly in the Azure Synapse SQL pool, along with the copy command, which is very similar to some things that Polybase does. And then there's other data movement operations, specific types of data movement that still have not been moved out of that service. But in essence, you don't really need to worry about that. You just need to know that it's there. There's not really anything that you can do about it. The other thing that the control node hosts is an Azure SQL DB, along with its own temp DB. And that temp DB is on SSD. But the Azure SQL DB is simply a shell database of our table definitions. It's going to hold our stored procedures. It's going to hold our functions, all that kind of stuff. It's going to have a schema of all of our tables and objects, but it's not going to actually house any of the data. It's a metadata shell. It also will hold statistics. Now, one of the questions, I call it aggregated statistics. If you're familiar with SQL Server statistics, a typical statistic will have a histogram with up to 200 steps in the histogram. Well, this control node still has 200 steps. And each individual distribution or database also has that statistic with 200 steps. So each one of those individual distributions will be aggregated together to come up with a final 200 step. It's not like we take 60 times 200 and that's how many histogram steps are in our shell database. That's not how it works. So that was our control node. And ultimately, for the most part, outside of some edge cases, everything goes through the compute node or the control node. When you submit a SQL query or any type of DML or DDL operation, it goes through the control node. And the control node decides how to push that down to the compute nodes. Now, each compute node will contain an Azure SQL DB, at least one Azure SQL DB or distribution. We'll call it distribution. That's the terminologies that we use in the Azure Synapse SQL pool. But for this presentation, I just decided to kind of keep referencing that ultimately it's a separate database at the lower level of the hierarchy. Now, we'll talk about DWUs in a minute, but when you look at them, everything up to and including 500 is a single node. And then as you get higher into the DWUs, we increase the number of nodes based on DW on 500. So for instance, we go from 500 directly to 1,000. Okay, so DW 1000 has 2 nodes. That means we have 60 distribution or 30 distributions each. So as we go up, each one of these has to be a multiple of 500, but it also has to be divisible. The number of nodes have to be divisible by 60, right? Or I'm sorry, well, 60 has to be divisible by the number of nodes. So ultimately, we go all the way up to a DW 30,000, which would be 60 nodes. And in that case, we have 60 separate nodes with 1 distribution each. The other thing that we have on each compute node is an NVMe temp DB, and each one has its own cache. Okay, so we chose, if you're using an Azure Synapse SQL pool, you're expecting a certain level of performance. That's why you came here, because you need a high performing data warehouse. And so having tempdb on NVMe storage is really beneficial. And then each node has its own cache as well. So this is a nice little layout and a graph of these DWUs. Now we shorten it to DWUs. Technically, DWU is from the first generation of this. We call these now CDWUs. But the acronym DW just gets thrown around because it's easier to say than CDWU. And ultimately you pay on what you chose to use, right? So at the compute level or the resource level, you're paying for what you choose your SKU to be, what level of DWUs. Now, these are linear going up. So as you can see, as I go from 600 or DW 1000 to 1500, I get another 300 gigabytes of RAM. As I go from 1500 to 2000, I get another 300 gigabytes of RAM. 2000 to 20. You see where I'm going here? It's linear. Same thing with the size of our temp DB. Goes up as we scale up. And then finally, our cache as well. Our cache is going to go up. And this cache is something called adaptive cache. And that is, I think Mark is going to touch on that in the next session. But we also will touch on it a little bit down here. It's a performance improvement that Microsoft put in to aid in the caching of column store index tables. That's simple. It helps our column store indexes. Okay. DWUs are a combination of CPU, RAM, and I/O. I know that's a difficult sometimes concept for customers to quantify, right? How much do I need? But an example that I'll give is typically, and again, this is typical, not, including the edge cases, which certainly exist. When I see a DWU total going up to, let's say, 80%, more than likely 70 to or 90 to 100% of that entire 80% is either due to CPU or RAM. Okay. And so it's pretty easy to see through some of the metrics how your Synapse SQL pool keeps up with this. And these metrics are readily available also in the portal in Azure. And so if you have any doubts about what you need to use, which most people do when they first get started, start low and then bring it up, right? Now, if you're worried about performance during production, start high and bring it down. But you can see pretty easily through metrics in Azure how much your utilization is and how to tweak it. There's also an Azure Synapse toolbox out on GitHub with a lot of different log analytics queries and workbooks and stuff like that, that is available for you to download and use. So I highly recommend taking a look at that. Understanding the architecture of how the MPP works is one thing, but we have to help it out, right? They gave us the architecture for the hardware and for the infrastructure. But now when we are designing our databases, we have to do a little bit of work on our own. Okay. And so part of that is understanding a couple of things, and one of these more than the other, and that is table geometries and indexes. So let's touch on that. There are 3 different table geometries. Some people call them distribution types. I like to call them geometries because one of them technically doesn't actually distribute data, at least it doesn't at its end result. And so this is how we account for the fact that our data is in different places. Number one, we have to tell it, what do we want to do with that data? How do we want to distribute it? Much like when we do partitioning in a regular database, we give it a value or some way to partition that data. Hash distributed tables are usually our most one of our most common tables in Synapse. Well, I shouldn't say usually. Ultimately, what happens is when data comes into a hash distributed table, we've defined a particular column that it is going to use, much like a partition key. It's going to use that column to split up our data. But in order to split it up, it applies a hash function to the values in that column. Now, the hash function is deterministic. And what do I mean by that? It means that a 1 is a 1 is a 1, kind of. As long as it's an integer, the integer value of 1 will always hash to the same value, which means it will always be inserted or placed into the same distribution. Okay. Hash distribution tables or hash distributed tables are commonly used for fact tables, our final landing place for our very large tables. As of right now, the hash distribution function can only operate on a single column. So if you have to do some type of concatenation to come up with a good choice for this, you would want to do that during your transformation process. It is data type dependent, and that's because it's a hash function. So the integer value of 1 will hash to a different value than the big int value of 1, or than the character value of 1. Now, we're not going to guarantee that it's going to end up in a different distribution, but we're not going to guarantee it's going to end up in the same. That hash function is kind of like a secret. And so I don't know what it's going to do. I don't particularly care what it's going to do. But it's important to know that 1 as an integer is very different than 1 as a big integer when that hash function has been applied to it. Okay. The other thing, just in general, to know about hash distributed tables is the idea here is not the same as it is in partitioning. When we design partitions for SQL Server, the idea is to push everything to one or a few partitions when we're designing queries. That is not the case here. We want all of our distributions to be hit so that we're spreading the work out between all of our compute nodes. It would be really bad to do something like partitioning on a specific day, because that means on Monday we're hitting distribution 1 constantly. On Tuesday we're hitting, and on the second day of the month, we're constantly hitting partition or distribution 2. And we're not splitting out the work. The whole point of the MPP architecture is to split out that work. And so we want to make sure that with a hash distribution key, we are getting an even distribution of our data. Okay, but there's a bunch more considerations there about hash distribution that I'm not going to go into here because we're just focusing on the architecture and the options. The other table geometry that is a distribution type geometry is a round robin. Now, this is the default. If you just say create table, it's going to be made a round robin. What a round robin does is it basically takes each row coming in and puts it to a different distribution. It doesn't mean that it's going to go like in order. It's not going to what's known as PDW node 0 and then 1 and then 2 and then 3 and going in a loop exactly like that. But what it does guarantee is that your data coming in will be distributed evenly across the distributions. We usually end up using this for staging tables. This is a very common paradigm for staging tables, because at that point, the idea is to get the data in as fast as possible. We'll worry about getting it to its final resting place later. And so we're optimizing for load. We'll also use this if there isn't really a good hash distribution key. And again, I'm not talking in this talk today about what is a good hash distribution key. That'll probably come in a later discussion, or there's some great blog posts out there. Okay. Now, because of the fact that we don't have to do any work to figure out where the data has to go, it just gets routed automatically as it comes in. It's more performant than a hash distribution in terms of loading data. And that's why we typically use it for staging. The last table type or table geometry is a replicated. Okay, now I'm not going to go into the details again of what actually happens with a replicated table, but what you need to know is at the end of the day, we use this because we keep a copy of it on each individual compute node. And so when we do joins of something that is distributed across 60 distributions, the data from the replicated table exists on or is available to each one of those distributions without having to move a portion of it from one distribution to another. Okay. Because of that, it's commonly used for our dimensions. Typically joined to a hash distribution table. At the end of the day, we might have many dimensions as replicated tables, and then one or more fact tables that are hash distributed. Replicated tables typically work best for data that is either static or slowly changing. And we like to say as a best practice, we like to keep them less than 2 gigabytes. That's not to say that there aren't tables that are a little bit bigger that aren't good candidates for it. At the end of the day, kind of what I say is the larger you get, the less you want it to change. In fact, a completely static table may be just fine replicated at a pretty large size if it never changes. And that's because of the way that this data gets replicated and cached. So now let's talk about indexes. At the end of the day, indexes in a Synapse SQL pool work the same. Heaps are the same. They're unordered sets of data. They're stored on pages. Clustered and non-clustered indexes work the same. They are B trees. They're stored on pages. One thing to note about pages in a Synapse SQL pool are that they're always compressed. They're always using page level compression. That's not just the default. You cannot change it. It's just the way it works. If you are using a row store index on a table, it's going to be compressed. So you don't have to worry about compression there. Column store indexes also work the same, mostly. There are some considerations that you have to take with your column store indexes. Now, in a Synapse SQL pool, they are the default. So again, create table, you're going to get a round robin, and it's going to be a column store, clustered column store. And that's because most of our analytics are going to be doing things like aggregations and things like that that clustered column store are very good at. Also, this is big data. We're going to be putting a lot of data in here. In order to get the most bang for our buck, we want to be able to eliminate as much data as fast as possible and compress it as much as possible. Now, I'm not going to go into the details of column store, but if you understand column store, you'll know that typically a column store index, we say that it's optimal at just over 1 million rows during batches and inserts. A row group, we want to maximize the basically filling it up, and that's going to be at a little bit over 1 million rows. However, we now have 60 column store indexes instead of just one. When we create a table with a clustered column store index, it's not 1 million rows. It's 60 million rows. And so if we're batching our inserts, what we're really looking for is 60 million rows in a batch, not 1 million. That doesn't mean that you can't do less, okay? Because the way that column store indexes work is, in a nutshell, it inserts into a B tree until it hits a limit, and then it compresses it into the column store, or it inserts it directly into the column store. And so if you're doing these kind of trickle inserts, we will fill up to 1 million, but it may take some design changes for performance from your side if you're not able to insert 60 million at a time. we do say, okay, well, you can get away with half, right? So we'll say 60 million is optimal, but we recommend at least 30 million rows for a table with a clustered column store. Again, that's a general recommendation. It doesn't mean that you're going to have horrible performance with less than that. It's just a general recommendation. My last point here kind of has a star there. And I know Kevin in his talk, he briefed on this a little bit too, that the optimal size for rows in a column store is pretty high. And that's true, but our adaptive cache is specific for column store. So on those edge cases where you can't get that much data into a column store to get those optimal row group sizes, you may still be getting a benefit by having them in a column store because they can use the adaptive cache. So depending on your use case, that may still be a good option for you. But in general, if your table is not going to be that big, then it may serve you better to do a normal row store clustered index on it that is going to use page compression and function that way, at least until it starts to get bigger. Or you can use a paradigm with a view over both of them. So, the other thing that's different is if you are familiar with column store indexes in SQL Server, reorganizing does a lot these days. It started out where it would reorganizing a column store would simply just close the open row groups, which are the Delta store, or merge the Delta store into the into a column store. However, they added a lot of functionality so that in SQL Server, you really don't have to do a rebuild these days. You just reorg and it takes care of everything. That is not the case in Synapse. Synapse did not pick up those changes. So reorganizing a column store index in Synapse SQL Pool only closes open row groups. Okay, and that's really important because you may have to do more rebuilds of those column store in Synapse SQL Pool. Of course, the paradigm is very different. We should be rebuilding those column store indexes after we load the data anyway. And it can be a part of our ELT or ETL process. So the last thing I will touch on here is data movement, because I've mentioned it a lot. And I just want to touch on this. So if we're storing all of our data in these different distributions, Jared, and so we've got no shared storage, well, how the heck do we get data from one distribution to the other if I join it? Well, that's what data movement is. Okay, so if I'm joining on two tables and part of the data, part of the rows that need to be joined from one table to another don't exist in that Azure SQL DB or on a different distribution, that's where the data movement service or the instant data movement has to come into play. We have to move some of those rows from one distribution to another. In fact, this is what plans look like from the control node. When you're used to looking at SMP plans or your SQL Server SQL plans, they talk about things like clustered index scan and table scan and spooling, right? Maybe even some order bys. And then we've got our nested loops, our hash, and our merge joins. That's not what you're looking at when you're looking at a distributed SQL plan or a DSQL plan, which is what comes from our control node. What our control node does is it tries to figure out the best way and the cheapest way to move data from one distribution to another when it's needed. Now, in a perfect world, we would never have to move data. We would have our replicated tables as dimensions. We would have a single fact table, or if we had two, they would both be hashed on the exact same data type. And that column is what's used in the join, but that's just not the real world. So what we want to do is we want to minimize data movement at the end of the day. But it is the primary cause of performance issues in a Synapse SQL pool. And usually that's because of picking the wrong hash key. Oftentimes because of what I said earlier, where people think about it like partitioning. And so they partition on date or something like that. By the way, date is a very poor, in general, and not always, but in general, like date is a really poor partition key in a Synapse SQL pool. Okay. So you got to kind of change the way you think. At the end of the day, to reduce data movement, you want to choose the right table geometry and hash distribution key to reduce that. You also want to make sure that your statistics are updated because that's how it makes those decisions. So statistics maintenance is very important here. One thing I'll note about that, we do not automatically update statistics in the Synapse SQL pool. Let me say that again. We do not automatically update statistics in the Synapse SQL pool. And as of today, there is still no way to enable automatic update of statistics in a Synapse SQL pool. You must update statistics on your own. So it's really important. Again, with an ELT process, we should build it into the process. Either we're rebuilding or we're updating statistics. So just a little kind of, I really like this slide from Microsoft, but what it shows is kind of a nice little demonstration about this data movement, right? So I'll give you this kind of general overview, especially if you haven't seen it before. The idea here is showing that we've got a fact order header table, okay? Which even though we wouldn't usually have a header detail in a proper star schema, but we're going to use this anyway. So we got an order table and we need to join it on the order detail, right? And so if this is hash distributed based on the order detail ID, and this is distributed on the order header ID, then more than likely whatever header ID is stored over here in the order detail table is not in line with our distributions here. So when I say I need to find all the detail records that fit order header 1, they could be all over the place here. So we have to move that data. We have to move it over here so that we can do a join. That's what data movement is. And so in this particular case, I might have said, well, fact order detail, we probably don't need to order by or hash on the order detail ID. In fact, who's going to search by the order detail ID? Nobody. They're going to group these things by the order header. And so if this one is hashed on order header, and I'm always joining these two based on the header ID, I would have chosen to hash distribute the order detail on the order header ID. And that would have reduced data movement. So it kind of works like this, right? We see this one as order header 1, 2, and 3, but yet 1's here, 2's here, 3's over here. And so these things can't actually join until we somehow bring that data there. And at the end of the day, in general, what the SQL pool does is it creates a temp table, brings all the data into it that it deems that it needs, whether it's from the order header side or from the detail side. It'll use statistics to figure that out and then throw it into a temporary table and join to the temp table. Right? So it'll move all that data into a temp table and now it'll join to it. As far as architecture about MPP and more specifically the Synapse SQL pool, that is all I have. And so I've left about 9 minutes for questions. Any questions?
You guys feel free to come off mute if you want to go ahead and ask Jared a question directly. Good session. Thank you very much.
Yeah, thank you for having me.
Oh, yeah. So about a couple of months ago, I shadowed Jared on an optimized SQL pools engagement. Really wasn't a class, right? It was more along one of those advisory type kind of customer engagements. I was like, oh, this guy's a good speaker. So I asked him to speak at the our event here, and I have no regrets whatsoever. Great session.
Yeah, thanks. Thanks so much. Yeah, I think Synapse SQL Pool is pretty cool. I love the idea of this distributed architecture, and I love designing it because it adds kind of another level to the puzzle that is good database design in general. Now we add this other layer onto it, and it just makes it, I don't know, for me more fun. You know, I'm a nerd, so that's why I'm here. That's why I like to speak. And yeah.
I get it. Well, it looks like some of the questions really, like Mark Price Mar was in the background answering some questions. So I don't see a lot of questions about this session. So I mean, that aren't addressed. So it looks like it's pretty good. So I'm going to go ahead and let me know. Are there any more questions, folks? I'm going to hit recording or hit stop record if there's not. Okay.